Okay, 9 o'clock, we'll start. So good morning, everybody. I'm Gene, WB9COY, and today we'll be talking about FSK and C4FM modulation. It's meant to be a primer, so we're not going to get really super deep, but we'll go through this a little bit of mathematics. So the motivation for this presentation was through a group I work with in San Diego. In this group, we launch high-altitude weather balloons for kids, high school projects, and we discovered a real gem called a radio sonde. And what that is, it's every day across the nation, then twice a day across the nation, the National Weather Service launches weather balloons, and attached to the weather balloon are these little devices here. It's a weather sonde. I'm going to pass this around so people can touch and feel. So this is like the motivation. Weather sonde. Sonde. Yes, that's what they call it, sonde, a sonding device. S-O-N-D. S-O-U-N-D? Oh, S-O-N-D-E. Yeah. S-O-N-D-E is a weather sonde. And this is actual one that we've actually got. So they transmit their signal on 400 megahertz, FSK modulation. And we track these things to the ground. It has a GPS on it, so we know where they're at. And there's a bunch of hams in San Diego that love these little geo prizes in the desert. And they'll go out there and they'll get these things. This is one guy, Randy, who's got a stack of 200. So he supplies us with all these little gems. It's got an ARM processor on it. It's got a GPS, a U-Blox GPS, very capable, and an SI432 RF deck, and a very high accuracy pressure sensor. We cannot reproduce this in our classrooms for $300-400. And here they are for free, falling out of the sky. So I've come up with a software build that repurposes these things to the ham radio frequencies. I use FSK modulation, and we've also added a camera. So later on, as an adjunct to this primer, I'm going to show you pictures of a radio sonde at 100,000 feet. So in the learning process of repurposing these things, I've come to knowledge on FSK and C4FM, because we use both, and I'll get into that. So I'm going to pass this around to the group. So Ray, you've already seen these. Don't be afraid to break it. There's 200 more in stock. But it's amazing that this hardware is just dropping out of the sky for free. So this is a classic FSK waveform on a spectrum analyzer, although this was done in MATLAB. And at the end of this presentation, we're going to know what FSK means, and actually C4FM. A lot of us use C4FM on a regular basis with DMR, P25, system fusion. These are all C4FM systems, and we're going to know what exactly that means by the end of this presentation. We're not going to get into the deep mathematics, but you will know what it means, what that C in front of that means. So this is an FSK waveform, and we'll talk about that in more depth. So we're going to do an introduction, some digital basics, FSK basics, C4FM specifics, and then we're going to compare and contrast FSK versus C4FM. And then we'll look at the FSK signal on a spectrum analyzer. I got some printouts and any questions you guys might have at the end. All right, so this presentation will address two very popular waveforms. It'll use in ham radio, FSK, 4FSK. The content will be at the beginner and intermediate level. Now, at any time, I find this more interactive with the folks who are interested. You got a question, just bring it up. Rather than trying to hold that question for the end, you may forget it. So go ahead and interact as you wish. And then the physical layer will be the emphasis of what we referenced today. And finally, I had to hand hand code the FSK waveform in that radio sound. It was very interesting, and I found, well, I've learned enough to maybe share with other hams. So this is the traditional C4FM. Well, actually, we'll lift it from the wiki, but we're gonna dissect this a lot more in the presentation. So I'll just read it, and then I'm going to kind of go over what the takeaways on this slide should be. Right, so C4FM refers to a particular symbol frequency deviation, and there's some numbers for you. Those are commercial standards from P25, APCO 25. Whereas the term FSK can reference a variety of different symbol frequencies and deviations. So then also a takeaway here is that there is no amplitude component in FSK and 4FSK and C4FM modulation. So that's an important takeaway. So if there's no amplitude component, we're only kind of discriminating on frequency. One tone or the other tone, two tones. We'll talk a lot about that later. Our amplifiers could be a lot more cheaper, less linear, and overall for the general consumer market, it's a better cost-effective way. So the amplifier only has to deal with a signal on a particular frequency rather than trying to replicate the entire amplitude waveform. So they're cheaper, they're nonlinear, typically Class C amplifiers. You guys are familiar with Class C? Yeah, that's what the door opens up for these cheap amplifiers. All right, then there we go. The term symbol, we're going to dissect that a little bit. Maybe some of you guys know what a symbol is, but remember it's at the beginner intermediate level. Symbol is not a bit, actually a symbol can be a bit, and we're going to talk about when a symbol is not a bit. And then we're going to further define what C4FM, that C in front of C4 is very, that it defines the standard, and I have a slide just dedicated to that. All right, terms, baud. So that's symbols per second. Sometimes it's bit per second, and sometimes it's not. And so we're going to dig into that, and I'm really hopeful that by the end of this presentation, you'll know what baud means in reference to our communication systems. And then C4FM, that's the big word right there, contiguous. Continuous, four-level frequency modulation. So I have a slide dedicated to that, and the contiguous thing is the important thing that separates regular 4FSK from C4FM. Deviation, that's just the distance between the center frequency and what we transmit. Well, the distance between the center frequency and a tone. DMR, digital mobile radio. FSK, frequency shift keying, and it uses two distinct frequencies. So the original slide we had up, that was FSK. FSK is sometimes called binary frequency keying, 2 FSK, or just plain FSK. They're all the same. So whenever you see FSK, it refers to two tones. And we're going to define what a tone is. 4FSK uses 4 discrete frequencies. And we'll get into why we want to use 4 instead of 2. What's the advantages, what's the disadvantages? Mark is carried over from the old days, corresponds to the high frequency and represents as a 1. And more terms, modulation index, that's a great way of just measuring how the quality of our modulation. 1 is the perfect number. And so we're going to do some calculations on that. P25 stands for Project 25. APCO 25 is a suite of standards. And it uses C4FM. Tone, that's just a carrier, just an unmodulated carrier, a tone. And FSK and 4FSK uses tones. And we don't take our voice and we flip it with traditional like Bofang FM modulation. In FSK, our voice gets converted from analog to digital, and then we modulate these tones based on our digital representation. got some slides on that. Space, that's just the low frequency, represents 0. A symbol, discrete state, and I've got a slide on that where we're going to see how, FSK symbol is, the bit and the symbol mean the same, but for FSK it's not. And we'll learn about that. And then YSF system fusion. So it kind of lays the groundwork. We've got some definitions, terms. So I'm going to take apart C4FM. What's that C in front of C4FM? So remember, C stands for contiguous 4-level FM. The top wave is a contiguous wave, and we see that these tones are, this wave is spaced together, so it's a higher frequency. So that's a 1, that's a 0, a 1, and a 0. Well, the lower waveform is the same 1, 0, 1, 0, but look at that discontinuity there. So our receive systems don't really kind of care about that a little bit, but our transmitter systems do. So this is contiguous. This is not contiguous. And remember I said about trying to keep our amplifications in our transmitter section cheaper? Well, this little discontinuity over here really causes havoc for our final amplifiers. We don't want these big shifts, and when we get these big shifts, that means we have to replicate that in a more qualified manner. If we do some, I'm just going to say, if you just take my word for it, symbol magic, if we do some symbol magic, we can avoid this discontinuity, and that's what C4FM does. That's C, and this is what we're trying to eliminate. And we can do that with our transmitter chain by doing some fancy symbol manipulation. So that's the intermediate level. So there's your C right there. That's what we want, and that's what we don't want. All right, deviation. So just explaining for beginner types. We have the FC, center frequency, and we have the frequency mark, frequency space. So it's just the distance between the center frequency. That's what deviation is. And the mark frequency is logic 1, and the logic 0 frequency, the space frequency, is the logic 0. So there's some math here. It's mark minus space divided by 2 is your delta. So a clear definition of what deviation is, because we're going to use this in some other math later on. Symbol. I want to dwell here to make sure everybody's got this, because I find in the wild hams can't get this symbol and bit thing straight. So FSK, 2 FSK, binary FSK, all the same. This FSK signal here, we have 2 states of the signal. We have mark and space. Each tone represents a bit, because we only have an alphabet of 2, right? There's only 2 tones there. So the high tone is a 1, and the low tone is a 0. At FSK, the baud rate and the bit rate is the same. All right, I'll go back to it if I have to. Now, this is the important part right here for 4 FSK. 4 FSK represents 4 tones. It can be C4FM, but not necessarily. 4 FSK is the more general term. Each tone represents, well, it's an alphabet of 4. So now I can represent 2 bits per symbol. So that's a symbol and that's a symbol. The representation in 4 FSKs that I can now transmit or represent, I can symbolize 2 bits per tone. So that tone, when it's transmitted and received, represents a 1, 1, 2 bits, 0, 1, 1, 0, 0, 0. 2 bits per symbol. That's the major takeaway. And there's going to be some math that supports this symbol rate calculation. But everybody got that one? All right, cool. All right, modulation index. How are we doing on time here? We're doing really good. So the number we want for this modulation index is 1. That's the perfect score. Everything is great. We want 1. So the formula for FSK is 2 times the deviation. We all know what deviation now is, distance from center, divided by data rate. Now remember, I'm using data rate here, not symbol rate. But guess what? In FSK, the data rate and the symbol rate, they're the same. So doing the math and solving for 1, which is our perfect score, we come up with a deviation to get a modulation index of 1, 4.8 kilohertz. And so that's what I did for the radio zone that we're passing around. I made sure that my deviation was at 4.8 kilohertz. So I have this modulation index of 1. Now it takes up a little more bandwidth to be perfect. It takes up a little more bandwidth. But that's what we strive for in our FSK implementation on the radio sound. Now let's go look at 4FSK. So now we got 4 tones. And the modulation index, we're solving for 1 again. So now we take the 2 outer deviation, divide it by the symbol rate, and it times it by m minus 1. So m is the 4 tones. So 4 minus 1 is 3. 3 times the symbol rate over 2 times the deviation. And solving, we come up with 7.2 kilohertz of bandwidth for 4FSK to be at a perfect modulation index. Now later on we're going to see that, well, why in the commercial world do we want to use more bandwidth than FSK? So let's back up 1 slide here. Notice FSK we had 4.8, and then for perfect score on 4FSK we got 7.2. Well, we can actually narrow so the commercial world, we actually decrease the spacing between the tones. Now we can squish more in a particular bandwidth. However, a modulation index doesn't look so good when we do that. So our receivers have to be a little more, there's a little more things, the receivers have to be more aware of that and figure out that, oh, I'm going to have some closer spacing, and that closer spacing actually is called inter-symbol interference, ISI. You'll hear that in radio terms quite a bit. So when we space those together, squish them together, we create ISI, and our receivers have to be, they got to be aware of this. And how they get aware of this is through forward error correction. I got a slide on that too. So we're always going to have this ISI problem when we start squishing stuff together. And I got slides that say, all right, this is what P25 is using. What's the modulation index of P25? I've got the calculations for that. Occupied bandwidth. So I'm setting up a story here. We got a perfect score. We got perfect deviations. Now what's the occupied bandwidth for perfection? And if we just plug in our numbers here, our occupied bandwidth for 4FSK at a bit rate of 90, I'm using 9600 baud on these radio zones. We do that, we come up with 19.2 kilohertz. And we've actually measured it. It was 20. And so that comes out pretty darn close. Geez, the math works. So we get a perfect score of 1, and we come up with 19.2 kilohertz of bandwidth for FSK. Now let's look at 4FSK. So here's the formula for 4FSK for occupied bandwidth, and taking all our perfect numbers, and we plug it in here, and we get, oh my gosh, we get the same bandwidth. But what's going on here? In the perfect world, our 00 is 7.2, the outer, for 0001, and 4.8 kilohertz. Anybody else want to see this? Didn't see this? You didn't see it?
I didn't catch
Okay, there you go. Maybe we could pass it to that gentleman back. Thanks, you. So notice here, symbol rate 4.8. Our bit rate on FSK was 9.6 kilobits. You divide by 2 because there's 2 bits per symbol. So now the symbol rate is half, but we still solve for the whole equation. You still come up with 19.2. We're going to reduce that number by quite a bit, and we're going to see how the math says, wow, we have a lot of ISI in there, but we can handle it. All right, here's some real world stuff. P25 versus YSF. YSF being system fusion. That's stuff that we use. I like it, actually. I use C4 at home, C4FM at home. So the commercial world, P25, this is the standard. Outer tones at 1.8 kilohertz, the inner tones at 600. And this is what Motorola, no, just not Motorola, but this is what the P25 standard says for what your C4FM signal should look like. Yaesu did something different. Their outer tone is 2.7 kilohertz, so it's a little wider. And then we do the math for occupied bandwidth using the implementations that we can buy off the shelf. That's the P25 Motorola stuff. This is System Fusion. We come up with a BT modulation index for P25 that's awful. It's 0.125. And so we can tolerate that because we're doing mathematics on the back end to correct all this stuff. Because now we're squishing that signal that used to be at 19.2 perfect signal. We're squishing it down to 8.4 to fit it in a 12.5 kilohertz channel. So we've got to be compatible with FM. So all the commercial channels are 12.5. I've got a little slide on that, 12.5 kilohertz wide. This is what we're trying to squish into there. So System Fusion has a better modulation index, 0.374, and so a little bit wider. And so that's the commercial implementation, that's the ham implementation for FSK, or in this case, C4FM, because both these schemes, P25 and System Fusion, use C4FM contiguous, not the non-contiguous, but contiguous. All right. So a little information on YSF. We're running ahead. So there's these modes called DN, VW, DW, and they're all going to fit in the 12.5 kilohertz channel. But what's going on here, this is just a FYI for the System Fusion guys. When we're in DN mode, so the misnomer I'm trying to explain is that, geez, when I switch from DN to VW, you don't get more bandwidth. Bandwidth stays the same. Your channel is still 12.5 kilohertz, whether you're a DN or VW. What happens is that this data error correction, this forward error correction stuff in here, gets chopped. And so now you're on your own. We dedicate the entire channel to digital voice. So what Yaesu is trying to say there, hey, if you got a clear path and you want to get a little more audio quality, because now the more bandwidth we take, the more fidelity we get in our voice, we can dedicate the whole channel to just digital voice when we have a clear path. We're not worried about skips and jumps and stuff like that. Maybe I'm on a repeater and I'm in and out. You definitely want to be on DN because you'll take advantage of the forward error correction that's transmitted as part of the signal. So this kind of clarifies what's going on with YSF and 12.5 kilohertz. And then there's other mode, if you ever have a picture camera, you send pictures back and forth. They haven't really revealed that API a lot, but it should be nice to exploit it. That's all dedicated to digital, the camera. So I got a little camera on my handheld, and I send pictures back and forth. So that's this DW mode. But mostly hams use DN and VW, and that's what's going on. Any YSF questions?
The wideband sounds really nice.
It does. Doesn't it sound nice? But the misnomer is that, oh, I'm taking up more bandwidth. Well, you're not. But it does sound nice. I think Yaesu's done a great job with that. I think they had a rough start, but I think they figured things out.
A lot better sounding than DMR.
Oh, yeah. Or DMR, right?
Yeah, it's a lot better than DMR.
Well, DMR is taking up 6.2 kilohertz of bandwidth. So guess what? You're right, though. You know, one-for-one comparison, how much voice you got in there, yeah, it just does sound better. Yeah, all right. So this is a big takeaway, a huge takeaway. So this is why we use 4FSK in the commercial world, in our ham world. 4FSK is more spectrally efficient. Notice I can squeak in with the commercial numbers, 8.4 kilohertz of bandwidth for P25, and then 13.2 kilohertz of bandwidth with FSK, using the commercial numbers. So I go back to the BT index of 1, we got a lot of bandwidth. But we can now squish that in and tolerate inter-symbol interference to the point where 4FSK is more spectrally efficient because we can squeak the tones closer together and still close the link in a proper manner. So that's the big takeaway from here. Why we use 4FSK? Because it's more spectrally efficient. So if anybody asks you that, that's your summary question.
Because the FCC wants you to go to 6.25.
Oh gosh, yeah, I know.
Beat us over the head with that.
More spectrally efficient. All right, here's a little hierarchy. C4FM as related to 4FSK. So 4FSK sits at the top of the food chain. Now we talked about the specialization, the C in front of C4FM, that's contiguous. So whenever we specify a 4FSK signal that's contiguous, doesn't have that anomaly in there, right? That phase shift that causes us to have more expensive amplifiers, we call it C4FM. So it's a derivative of 4FSK. And then within C4FM, we have P25 and system fusion. Now we have DMR sitting off to the side. It's also 4FSK, but it's time division, so it's no longer contiguous. So the channel is still 12.5 kilohertz wide, but we have these time slots now in DMR, and that disqualifies it from being a C4FM, but DMR is a 4FSK system. So I'll put that in there for notes. Okay, just a final review before we go into like comparisons of the two. 2FSK, 2 tones, and then 4FSK, 4 tones, and then each tone has we put symbols in 4FSK, bits in 2FSK. And there's a graph that may be interesting to you, all right? So it's not signal to noise that's doing this. So 4FSK is actually less sensitive than FSK because we're getting inter-symbol interference. As you move those symbols closer together, guess what? They interfere with each other, causing receiver sensitivity issues. We can correct those using mathematics. I got a slide on that. Maybe with Reed-Solomon algorithms or stuff, where we're starting to use mathematics to correct this 2 to E. But out of the box, this is how the curves look. It's about 2.2 dB of difference between FSK and 4FSK. And the reason why we use 4FSK is because of bandwidth. It's more spectrally efficient, nothing's for free, and the thing that we give up is sensitivity. But we make up for it. Let's see. I'm going to move to this slide. I'll move back. So this is how we make up for it. We use an SDR, software-defined radio. We demod, and so this is a leap of faith. Remember intermediate to beginner class? We go from SDR to demod. There's a lot of stuff going on in between here, but we get 1, 0, 1, 0, 0. All these, it's all that's coming out of an FSK, 4FSK system is zeros and ones. We rely on analog to digital converters to take our voice and put it into digital. Those A and B vocoders you've probably heard about. So we get nothing but zeros and ones, and then that demod is fed into a decoder. And typical decoders will sync on or look for a preamble, look for a sync, and look for payload. So what does all that mean? So this is actually a preamble right here. I put it up there on purpose, right next to preamble. 0, 1, 0, 1, 0, 1, 0, 1. Those receivers are looking for that pattern. When it sees that pattern for so many bits, boom, I got a lock. So I got a preamble. But I still don't know how I can get on the train. I see the train, but which car am I supposed to get on? We do a sync. And so that sync says, boom, we've now got sync. So there's a sync word that gets transmitted in there, only at the intermediate level, so we won't go deeper than that. But just know that there's a preamble, 0, 1, followed by a sync, and then the payload. So that payload gets shipped over to forward error correction. A typical forward error correction mathematics that are used is Reed-Solomon. Very, very, very famous mathematician. And so any errors that we've encountered by squishing those symbols together and getting our receiver less sensitive, we start making up for it in mathematics. So we know we can get back to ground zero, maybe even improve it by a lot of back-end processing. And your cell phones always work on about a 1 to 2% error rate. If it's not working at that rate, you're transmitting too much power. And so forward error correction is part of these schemes to get good packets. All right, so this is now real-life stuff off of a 4FSK radio sonde. So the sonde that I passed around, that is using 4FSK. That's what the Weather Service uses. The chip is the SI432 chip that's in the sonde is native to FSK. There's a group in Australia. Mark, I forgot his name right off the hand. Mark Jessup, very famous in the high altitude weather ballooning area. He has implemented a 4FSK system for the radio sonde. The same sonde that we passed around can also work 4FSK, but he's manually creating the waveform himself from scratch. Carrier on, timing, carrier off, change frequency, carrier on, carrier off. So this is actually a plot of Mark Jessup's radio sonde, and you can see, if you're getting interested in high altitude weather ballooning, there's a site called Sonde Hub, S-O-N-D-E Hub, Sonde Hub, that Mark has created for all the ballooning people in the world, and literally you'll see maybe 20, 50 balloons in the air, all using radio sondes that have been recovered from the Weather Service. It's becoming kind of a popular thing. So here's your 4 tones. I mean, if nobody believed me, here's a real chart. It's actually transmitting 4 tones, and those tones operate, they're symbols. Each one of these tones represents 2 bits, and so that bit stream just comes to us in that manner. So that's getting we got 5 minutes left. And so I got some fun stuff. So this is that radio sonde that you saw floating around that's using FSK. So this is my implementation. I'm able to actually squeak a camera in that sonde, a cheap Chinese camera. You carve out the styrofoam in that case, and I get a camera in there. So we do projects with kids, and high school kids in San Diego, We get these weather zones that typically land in the desert areas in back of San Diego, Salton Sea area. These geo prizes are collected by hams with 4-wheel drives. We get them back and we launch them with the high schools. So it used to be these high altitude weather balloons. It cost $300-400 for a payload. And if you lose them, it's a woe is me. And we always had to plan our flights really particular. The winds had to be just right. And the kids had to be available on that day for the flight. So we didn't get many flights in. But with these weather zones, we don't care. We got them for nothing. Poof, just let them go. And wherever they land, they land. So this is about 90,000 feet. See the curvature of the Earth. It's got a little bit of a dingle over here. My forward correction was exceeded there. But this is a picture from a radio zone using FSK. This is we've improved our sensitivity on these systems to the point where we're actually now seeing the sound on the ground. Now this is an area that is inaccessible. We're not going to go hiking back there to get it, so it just died a nice death right there. But we got pictures back of where it landed. And so I thought I'd just show that to you. So the high altitude pictures, we have a on the ground picture of a radio zone that, just before it took its last milliamp. And this is the pride and joy. We've got this down to launching those small. Who's got the zone right now? Some people walked in. Okay, some people walked in. So using FSK on this is a radio zone. This is attached to a weather balloon. Twice a day it goes up, and we get our 10-day forecast from these weather zones. And ham radio operators can repurpose it. We used to have payloads that weighed almost 2 pounds. Batteries, cameras, Raspberry Pis. We had radar detectors on a radar reflector. And when it all added up, it was a big balloon taking a lot of helium. Very expensive flight. And we didn't get them all back. Now, with the weather zones, the kids are doing all this work by themselves because this is all they have to deal with. It's a very small fill on the helium. They do all the work themselves, and they get on the websites. They track where the balloon is at. They look at the pictures. We do science. We collect pressure data, altitude data, and it becomes a nice doable do, all because of FSK on these little weather zones. So that was the inspiration of comparing and contrasting 4FSK to FSK, the things I've learned on my journey, and the payback through STEM. So I think that brings us up 1 minute. So you guys got any questions? You'll see this at the swap meet tomorrow. No, I'm just kidding. You guys good? Yes, sir.
What frequency are you on? You changed the frequency on it.
Yes, so the original frequency coming out of OEM is 400 megahertz. But I've easily just reprogrammed the PLL. We're on 431.05. So we're out of the satellite band for those satellite folks. We're not there. Don't want to be there. 431, it's actually, we coordinated through Scrubba in San Diego. In Southern California, we have a group called Scrubba.
Yeah,
The repeater group. So we got coordinated for that frequency. So try to be as up and up as possible. It's low power, but we're getting distances over 200 miles out of these things. So the normal launches, we fill enough helium in this thing to go up, get our nice pictures from 100,000 foot, and then they drop. Maybe they're by 50 miles away. But we've also done it where we barely fill them up. And we've got this thing going all the way to Phoenix one time from San Diego. And still decoding the signals that far away, 300 miles away. It's amazing. It's like a little satellite in the air.
How many watts?
Plus 17 dBm, so it's 3 dB below 100 milliwatts. Crazy. And it runs on 2 AA batteries. Lithium, you have to use lithium in here because of the temperature. But what a cool FSK project that was. So I'm going to let it to the next speaker. If you guys are good, we'll close it here. Oh, one more.